Welcome to our channel. We are so glad you found your way here. Let us help you fall asleep. Let's begin with ball lightning, the unsolved mystery of atmospheric electricity. Take a slow, deep breath in and release it. Let the weight of the day fade away as we embark on an unhurried, atmospheric journey through the wonders of the cosmos. Your mind is quiet, the universe is vast, and we are ready to explore. Ball lightning is a rare and enigmatic atmospheric phenomenon, characterized by luminous, spherical objects that appear during thunderstorms. These entities often float in the air, exhibiting unpredictable movement and sometimes vanishing without a trace. Historical accounts span centuries, with reports emerging from diverse cultures, each describing similar glowing spheres. They have been observed inside structures, hovering near windows, and occasionally interacting with individuals, leading to various interpretations and folklore. In the 19th century, scientific inquiry began to take shape, offering initial attempts to categorize this phenomenon. Researchers documented instances, noting their elusive nature, which brought skepticism and intrigue alike. Some early explanations suggested that ball lightning was merely an optical illusion or a product of combustion. Despite rigorous study, definitive conclusions remained elusive, leaving many questions unanswered. Modern science has embraced advanced technology to investigate these occurrences further, including high-speed cameras and atmospheric sensors. Laboratory recreations have attempted to mimic conditions that might generate ball lightning, yet these experiments yield inconsistent results. Observations continue to emerge, with first-hand accounts providing tantalizing glimpses into this atmospheric mystery. The complexities of ball lightning challenge established principles of physics, inviting both scientists and enthusiasts to explore the depths of atmospheric electricity's uncharted territory. Each encounter contributes to an evolving understanding of nature's unpredictable phenomena. Historical records depict ball lightning as a phenomenon that has intrigued humanity for centuries. Accounts of these luminous orbs appear across various cultures, often steeped in folklore and steeped in superstition. Descriptions reveal a range of appearances, from glowing spheres drifting silently through the air to erratic movements that evoke both wonder and fear. Ancient texts, such as those from China and Europe, recount sightings that often coincided with thunderstorms, linking the occurrences to divine or supernatural forces. As society advanced, the pursuit of understanding this phenomenon transitioned from myth to scientific inquiry. In the early 19th century, notable figures began documenting their experiences, including the renowned physicist Michael Faraday. His investigations laid groundwork for a more systematic examination of atmospheric electricity. Observations shifted from anecdotal to experimental as researchers sought to replicate the elusive nature of ball lightning. Modern science endeavors to decipher its mechanisms, employing sophisticated technology to capture fleeting glimpses of these enigmatic forms. Despite advancements, the underlying processes remain largely uncharted, presenting a paradox of knowledge and mystery. Each new observation adds layers to the complexity, bridging the realms of folklore and empirical study. This ongoing quest reflects humanity's deep-seated curiosity and the desire to unravel the intricacies of electrical phenomena in the atmosphere. Typically, ball lightning exhibits a range of sizes, from that of a marble to as large as a basketball. These globes of luminous energy may appear spherical, yet reports also describe variations in shape. Some exhibit an elongated or irregular form, the size and shape remain inconsistent across sightings, lending to the enigmatic nature of this phenomenon. Duration tends to be fleeting, with most instances lasting mere seconds. Observers often note that while the luminous sphere hovers or moves, it can seem to defy gravity or navigate obstacles with apparent ease. This behavior adds an additional layer of complexity to the understanding of ball lightning. Color variations are also frequently reported, with hues ranging from bright white to deep orange, and in some instances, striking blue or green. These colors can shift as the phenomenon dissipates, contributing to the mystery surrounding its composition. The temperature of ball lightning remains under investigation. Some accounts suggest it possesses a heat that can ignite surrounding materials, while others report a coolness, challenging preconceived notions of electrical discharges. These contrasting reports highlight the need for more rigorous scientific inquiry into the physical properties and underlying mechanisms of this atmospheric curiosity, which continues to intrigue researchers across disciplines. The elemental composition of ball lightning remains an enigma, with various studies suggesting a range of chemical constituents. Measurements indicate the presence of silicon, iron, and other trace elements, which may originate from the surrounding environment. This phenomenon typically manifests during thunderstorms, where intense electrical activity could facilitate the formation of these particles. Reactions between atmospheric gases, particularly oxygen and nitrogen, may lead to the creation of transient species that contribute to its unique properties. Preliminary analyses suggest that carbon compounds, possibly in the form of soot or vaporized materials, could play a crucial role in its appearance. The interaction of these elements with high-energy electrical discharges raises questions about the stability and longevity of ball lightning. Intriguingly, some observations have documented the spontaneous combustion of nearby materials during or after the appearance of ball lightning, suggesting that exothermic reactions may accompany its existence. The resulting chemical processes could release energy sufficient to sustain the phenomenon for durations that defy conventional understanding. Further investigation into these reactions may reveal not only the elemental makeup of ball lightning, but also the energetic pathways that allow it to persist in the atmosphere. Continued research will be essential for unraveling these mysteries, contributing to a more comprehensive understanding of this captivating atmospheric phenomenon. The theoretical models of ball lightning have emerged from a blend of historical observations and scientific inquiry. Initial concepts proposed by early researchers suggested that this phenomenon could be linked to the behavior of atmospheric electricity during thunderstorms. Various hypotheses have sought to explain the glowing spheres, with suggested mechanisms ranging from ionized air to the existence of miniature plasmas. In the mid-19th century, scientists began to document the fleeting appearances of ball lightning alongside lightning strikes, noting its peculiar characteristics. These early observations led to the idea that the phenomenon might be a form of electrical discharge, distinct from traditional lightning. As research progressed, the concept of ball lightning transitioned from anecdotal accounts to more structured scientific inquiry. Developments in the field of plasma physics began to influence theories, with some models positing that ball lightning consists of a self-contained plasma structure that can sustain itself for brief periods. The understanding of electromagnetic fields has also been integrated into the discourse, with suggestions that these fields could stabilize the ball lightning, allowing it to persist longer than expected. Recent advancements in computational simulations offer a new avenue for exploring these models. Through detailed simulations, researchers can recreate the conditions under which ball lightning might form, providing valuable insights into its behavior and characteristics, even if definitive answers remain elusive. The role of atmospheric electricity in ball lightning formation is a pivotal area of inquiry. The phenomenon often appears during thunderstorms, a time when electrical discharges are abundant. This environment provides the necessary conditions for the accumulation of charge, facilitating unique interactions. Researchers have noted that the presence of strong electric fields can influence the behavior of charged particles, possibly leading to the creation of these luminous spheres. Ionization plays a crucial role in this process. In thunderstorms, the air becomes ionized, allowing for the movement of electrons and ions. This ionization may contribute to the stability of ball lightning, allowing it to maintain its form for extended periods. The exact mechanism by which this stability is achieved remains a point of contention among scientists. Observations suggest that certain atmospheric conditions, such as humidity and temperature gradients, could enhance the likelihood of ball lightning emergence. This region of research also explores the impact of environmental factors. Variations in terrain and atmospheric composition may alter the characteristics of ball lightning. Certain locations, with their unique geophysical properties, exhibit more frequent occurrences, hinting at a complex interplay between localized atmospheric conditions and electrical phenomena. Investigating these variables is essential for a comprehensive understanding of ball lightning and its relationship with atmospheric electricity. Distinct from other atmospheric phenomena, ball lightning exhibits unique characteristics that set it apart from lightning, sprites, and other electrical discharges. While traditional lightning manifests as a brief flash, ball lightning may linger, floating or darting with an unpredictable motion. Its appearance can vary dramatically in size and color, sometimes resembling a glowing orb. Yet, unlike the linear path of a lightning bolt, it defies conventional trajectories. Sprites, forming high above thunderstorm clouds, emit short-lived bursts of light, whereas ball lightning can occur independently of storm systems. This independence adds to the intrigue of its behavior, as it has been reported during calm conditions, indicating a complexity in its formation that remains poorly understood. Research suggests that ball lightning may share some properties with other electrical phenomena. For instance, both ball lightning and lightning are thought to arise from ionization processes in the atmosphere. Yet the mechanisms behind these formations diverge significantly. These distinctions highlight the necessity for continued exploration in atmospheric science. Understanding how ball lightning interacts with its environment could reveal insights into the underlying physics of electrical discharges. The quest to unravel its enigmatic nature continues, as scientists aim to clarify the similarities and differences that define this elusive atmospheric phenomenon. Documented observations of ball lightning events provide a fascinating glimpse into its unpredictable behavior. One notable case occurred in 1946, when a group of witnesses in a rural area reported seeing a glowing sphere drifting through the air. This object hovered momentarily before vanishing, leaving behind an unmistakable sense of bewilderment. Such encounters often lack concrete explanations, with variations in color and size reported across different witnesses. Another incident in 1972 involved a similar phenomenon during a thunderstorm. A glowing ball approached a house, illuminating the surrounding environment with an eerie light. It reportedly floated through an open window, causing minor electrical disturbances before dissipating into thin air. These accounts highlight a common theme: the transient nature of ball lightning, often appearing for mere moments yet leaving lasting impressions on those who experience it. Laboratory experiments have attempted to replicate the conditions under which these phenomena occur. Researchers have induced ball lightning-like effects in controlled environments, yet the results remain insufficient to fully mirror the natural occurrences reported. Despite advances in atmospheric science, the enigmatic characteristics of this phenomenon persist, evading complete understanding. Each case study contributes to a growing body of evidence, each adding layers to the intricate puzzle that is ball lightning, a subject still shrouded in mystery. Cultural interpretations of ball lightning span centuries, weaving through the folklore and beliefs of various societies. Ancient civilizations often viewed this phenomenon as an omen or message from the gods. In some cultures, flashes of light in the sky were seen as manifestations of divine wrath or favor, imbuing the phenomenon with a spiritual significance that transcended mere physical occurrence. Legends depict ball lightning as a harbinger of change, a symbol of transformation that heralded significant events. In rural communities, encounters with these luminous spheres sometimes signified impending storms or natural disasters, reinforcing the connection between atmospheric phenomena and human experience. In literature, ball lightning has inspired countless tales, often personified as mystical beings or spirits. These narratives capture the awe and fear associated with the unpredictable nature of this electrical phenomenon. The imagery evokes a sense of wonder, reflecting humanity's long-standing fascination with the unknown. Artistic representations often depict it as a gentle glow or a fiery orb, illustrating both its beauty and its potential danger. Each interpretation enriches the cultural landscape, demonstrating how humanity grapples with the enigmatic forces of nature. They serve as reminders of the delicate interplay between science and belief, where understanding and myth converge, offering insight into the human condition amidst nature's mysteries. The study of atmospheric electricity reveals the fundamental processes underlying lightning formation. Lightning occurs when electrical charges accumulate in clouds, creating a complex interaction between positive and negative ions. This phenomenon begins with the movement of water droplets and ice particles within a cloud, resulting in collisions that transfer energy. These interactions generate static electricity, leading to the buildup of charge. When the electrical potential between areas becomes sufficiently large, a discharge occurs. This discharge manifests as a brilliant flash, traveling between clouds or from cloud to ground. The path of this discharge is influenced by the atmospheric conditions, such as humidity and temperature, which affect the electrical properties of the surrounding air. As the discharge travels, it rapidly heats the air, causing it to expand violently, resulting in the sound wave known as thunder. Research into lightning has also uncovered various types, including cloud-to-ground, intracloud, and intercloud lightning. Each type presents unique characteristics and behaviors, shaped by the dynamics of the storm system. Instruments such as lightning detection networks and satellite imagery provide invaluable data, enabling scientists to enhance their understanding of this natural phenomenon. The ongoing exploration of lightning continues to deepen knowledge, revealing intricate connections between atmospheric processes and the environment. Thunderstorms serve as a critical backdrop for the formation of ball lightning, an enigmatic phenomenon that challenges conventional understanding of atmospheric electricity. Within these storm systems, conditions can become ripe for the emergence of this mysterious entity. Where intense electrical discharges occur, the interplay of charged particles in the atmosphere creates an environment conducive to the generation of localized electromagnetic fields. As a storm develops, the rapid ascent of warm, moist air collides with descending cool air, establishing a turbulent mix that facilitates the buildup of electrical potential. When the threshold is reached, a discharge may occur, resulting in the familiar jagged flashes of lightning. In some instances, this process may give rise to the less understood spherical form of lightning, often observed as glowing orbs that hover or dart unpredictably. The duration and intensity of thunderstorms directly influence ball lightning formation. These ephemeral orbs may appear during the latter stages of a storm, often characterized by low visibility and dissipating rain. Observations indicate that they can manifest near the ground or within structures, suggesting a complex interaction with the surrounding environment. This phenomenon remains elusive, with few comprehensive scientific explanations. Investigating the correlation between thunderstorms and ball lightning continues to be a focal point in atmospheric research. Seeking clarity in this captivating atmospheric mystery, the connection between ball lightning and Earth's magnetic field offers intriguing avenues for exploration. Magnetic forces, ubiquitous in nature, may play a crucial role in the formation and behavior of these enigmatic phenomena. Observations suggest that ball lightning often appears in regions with heightened electromagnetic activity, hinting at a complex relationship. In the presence of strong magnetic fields, charged particles can behave unexpectedly. This region of influence may create conditions where ball lightning manifests, possibly through the entrapment of ionized gases. The alignment of charged particles with magnetic lines of force could facilitate the stability of these luminous orbs, allowing them to persist longer than one might anticipate. Research indicates that the intensity of Earth's magnetic field varies across different geographical locations, potentially influencing the frequency and characteristics of ball lightning sightings. Areas with anomalously high magnetic activity, such as regions near volcanic formations or tectonic boundaries, have reported increased occurrences. Additionally, the interactions between atmospheric electricity and magnetic fields in thunderstorms may lead to unique energy discharges, setting the stage for ball lightning's emergence. The examination of these interactions allows researchers to postulate about the underlying mechanisms that create and sustain this phenomenon. Continued scrutiny of these alignments may reveal deeper connections between atmospheric conditions and the elusive phenomenon. Temperature and humidity play critical roles in the formation of ball lightning, influencing the behavior of charged particles. Elevated temperatures can increase the kinetic energy of molecules, facilitating the collision and ionization processes necessary for creating these luminous orbs. This energy manifests as variability in electrical discharge, leading to unusual atmospheric phenomena. In humid environments, water vapor contributes to the formation of charged particles, enhancing the conductivity within the atmosphere. High humidity levels allow for increased collision rates among atmospheric molecules, which can foster the conditions needed for ball lightning to emerge. The interaction between water droplets and electric fields can generate localized areas of intense energy where the strange orbs may form and persist. Temperature inversions, where a layer of warmer air traps cooler air beneath it, also contribute to these phenomena. Such inversions can create stable, charged regions in the atmosphere. These regions encourage the accumulation of electrical energy, potentially resulting in sightings of ball lightning during thunderstorms or other atmospheric disturbances. The intricate interplay of temperature and humidity underscores the complexity of electrical phenomena. Each climatic variable adds a layer of depth to the ongoing investigation into this enigmatic aspect of atmospheric science. Understanding these relationships is vital to unraveling the enduring mystery of ball lightning. Topography plays a significant role in the occurrence and characteristics of ball lightning. Variations in elevation, terrain, and geological features can influence atmospheric conditions, leading to distinct manifestations of this elusive phenomenon. In regions with rugged mountains, for instance, localized air currents and unique pressure gradients may create environments conducive to the formation of these luminous orbs. The interplay between landforms and weather patterns results in a complex landscape where ball lightning might emerge with differing frequencies and intensities. Valleys, with their enclosed spaces, can trap electrical charges, potentially fostering conditions ripe for ball lightning. Conversely, open plains may allow for broader dispersion, altering the dynamics of electrical discharges in the atmosphere. Certain geological materials, like quartz, have shown potential to generate piezoelectric effects under stress, contributing further to the mystery. Areas rich in such minerals could become hotspots for ball lightning events, as the interaction of minerals with electric fields may catalyze their formation. Elevation also affects humidity and temperature, factors that are crucial in the development of atmospheric electricity. In higher altitudes, where air pressure is lower, the behavior of electric fields can differ markedly from that at sea level, thus influencing the likelihood of ball lightning occurrences. Understanding these intricate relationships can guide future research into this captivating atmospheric phenomenon. Laboratory simulations of ball lightning provide a controlled environment to explore this elusive phenomenon. Researchers employ high-voltage discharges to recreate the conditions believed to produce these luminous spheres. Specific setups involve the use of high-frequency electromagnetic fields, allowing scientists to manipulate variables such as temperature and pressure within a confined space. These experiments often take place inside plasma chambers, where ionization can be induced under various atmospheric conditions. By adjusting the gas composition, researchers can examine how different elements influence the stability and behavior of these transient entities. Observations indicate that the luminous quality of ball lightning may correlate with the presence of certain trace gases, further complicating the understanding of its formation. Measurements in these environments reveal a plethora of data, including the duration of the phenomenon and its electromagnetic signatures. Such metrics provide essential insights into the energy dynamics at play. Some experiments have even attempted to observe the interactions between ball lightning and solid surfaces, shedding light on its potential effects on surrounding materials. Each simulation aims to replicate the randomness and unpredictability that characterize natural occurrences. As these studies progress, the intricate nature of ball lightning continues to challenge conventional scientific paradigms, inviting further exploration and inquiry into its mysteries. Dust and aerosols play a significant role in the formation and behavior of ball lightning. These microscopic particles, suspended within the atmosphere, provide a medium through which electrical charges can interact. When atmospheric conditions are favorable, the presence of dust can enhance the likelihood of ball lightning occurrence by acting as nucleation sites for ionization. This interaction creates localized areas of intense energy, which can manifest as glowing spheres. The composition of dust and aerosols influences the characteristics of ball lightning. Mineral particles, organic compounds, and even pollutants contribute to variations in color, size, and duration of these phenomena. When high-energy discharges occur, they may interact with the particles, leading to the excitation of their atoms and resulting in the vibrant hues often reported by witnesses. Environmental factors, such as humidity and temperature, further modulate the behavior of these particles. Elevated humidity can increase the likelihood of ball lightning formation as water vapor interacts with aerosols, facilitating charge accumulation. Wind patterns can also play a role, dispersing or concentrating dust and aerosols, thus affecting the dynamics of electrical discharges. Research into the interaction between ball lightning and atmospheric particulates remains ongoing. Understanding these connections can yield deeper insights into the mechanisms driving this elusive phenomenon. The discourse surrounding the nature of ball lightning is marked by two primary theories: plasma formation and chemical reactions. Plasma, a state of matter comprised of ionized gases, is often proposed as the explanation for the glowing armed floating orbs that appear during thunderstorms. This region of atmospheric electricity suggests that the intense electric fields may create conditions ripe for plasma generation. The behavior of these luminous entities, including their ability to levitate and exhibit erratic movements, aligns with the characteristics of plasma, further fueling this hypothesis. Conversely, some researchers advocate for a chemical reaction-based model. This perspective posits that specific combinations of atmospheric gases, when subjected to electrical discharges, can produce the observed phenomena. Such reactions could lead to the formation of transient structures composed of various molecular compounds, capable of creating the distinct visual effects associated with ball lightning. These theories are bolstered by anecdotal observations linking ball lightning to trace elements in the environment, suggesting a complex interplay between local chemistry and atmospheric conditions. Each theory presents compelling evidence, contributing to a broader scientific investigation. The absence of definitive conclusions invites ongoing exploration into the nature of these enigmatic orbs. Understanding their origins, whether rooted in plasma dynamics or chemical reactions, remains a key objective within the field of atmospheric science. Continued research may eventually illuminate the intricate processes that govern this extraordinary atmospheric phenomenon. Quantum theories present a fascinating lens through which to examine the enigmatic nature of ball lightning. At the subatomic level, interactions between charged particles can yield unexpected behaviors, challenging conventional understandings of electricity and magnetism. When investigating this phenomenon, researchers consider the possibility that quantum fluctuations may play a role in its formation, leading to transient energy states that manifest in peculiar ways. And this region of study, the behavior of electrons and their arrangements within atoms, becomes crucial. Electrons, influenced by external electromagnetic fields, may enter excited states, releasing energy in forms not typically observed in standard atmospheric conditions. This energy could contribute to the unique visual properties of ball lightning, which often appears as glowing spheres or orbs, each exhibiting distinct colors and luminosities. Additionally, theories suggest that entanglement may be involved in the interactions that produce these luminous entities. The relationship between particles, even at great distances, could mean that changes in one particle may instantaneously affect another, potentially explaining the observed behavior of ball lightning in relation to surrounding electrical phenomena. This exploration of quantum mechanics not only expands the understanding of ball lightning, but also offers insights into broader applications in atmospheric science. Understanding these subatomic interactions may lead to new advancements in technology and energy management, reshaping perspectives on electricity itself. The manipulation of electromagnetic fields plays a crucial role in the characteristics of ball lightning. Observations indicate that these phenomena often occur in environments where electromagnetic activity is heightened, such as during thunderstorms or near power lines. The presence of strong electric fields appears to influence the stability and movement of these luminous spheres, creating a unique interplay between energy and matter. Research suggests that varying electromagnetic fields can alter the behavior of the plasma that forms within ball lightning. These fields may dictate the size and duration of the phenomenon, leading to differences in appearance and longevity. The interplay between charged particles and electromagnetic forces contributes to the distinct qualities that define each occurrence, ranging from color variations to changes in brightness. In regions where ball lightning has been frequently reported, magnetic fields are often unusually intense. This relationship raises intriguing questions about the underlying mechanisms that govern such a remarkable occurrence. The ability to harness or replicate the conditions that give rise to ball lightning could potentially unlock new avenues in energy generation or storage. Understanding how electromagnetic fields interact with atmospheric electricity will expand knowledge of these enigmatic phenomena. This exploration may not only illuminate the nature of ball lightning, but also contribute to broader advancements in atmospheric science and the fundamental principles of electromagnetism. Advances in imaging technology play a crucial role in the ongoing quest to capture elusive phenomena such as ball lightning. High-speed cameras, capable of recording at thousands of frames per second, provide unprecedented opportunities to analyze transient events. These devices reveal intricate details often obscured in conventional footage, enabling researchers to study the behavior and properties of electrical discharges with enhanced clarity. Thermal imaging systems further augment this investigation, allowing for the detection of heat signatures associated with ball lightning. This capability helps differentiate between various forms of atmospheric electricity and provides insights into temperature fluctuations that accompany these occurrences. Enhanced sensitivity in capturing light in different wavelengths, particularly in the ultraviolet and infrared spectra, adds layers of understanding to the nature of these enigmatic orbs. Field experiments utilizing drone technology also facilitate the observation of ball lightning in situ, providing aerial perspectives previously unattainable. This approach offers a unique vantage point, allowing for comprehensive data collection over extensive areas. Integrating advanced computational techniques, such as machine learning algorithms, enables the analysis of vast amounts of footage, pinpointing patterns that may reveal the underlying mechanisms of ball lightning formation. Such technological strides not only foster a deeper comprehension of atmospheric phenomena, but also hold the potential to refine our understanding of related electrical phenomena. Insights gained may enhance understanding of the peculiar phenomena surrounding ball lightning. The role of sound and light in these observations is particularly significant, offering clues that elude traditional scientific analysis. Often reported as a low-frequency rumble or a hum, acoustic emissions accompany the appearance of these luminous orbs. This auditory characteristic suggests a complex interaction between atmospheric electricity and surrounding air molecules. Light manifests in various forms during ball lightning events, ranging from soft glows to intense flashes. Photometric analyses indicate that these emissions may vary with the object's size, composition, and environmental conditions. The spectrum of light emitted, often described as an eerie luminescence, is critical for researchers attempting to decode the origins and behavior of ball lightning. In some instances, this light appears to pulse rhythmically, correlating with nearby electrical activity. The spatial and temporal relationship between sound and light provides a unique perspective on the dynamics at play. Studies suggest that these emissions might influence human perception, leading to misinterpretations or exaggerated descriptions. Understanding the interplay of sound and light could lead to breakthroughs in unraveling the complexities of ball lightning. Such insights may not only clarify its nature, but could also provide a deeper comprehension of atmospheric phenomena, bridging gaps in current scientific knowledge. Each observation contributes to a larger puzzle, slowly revealing the enigmatic workings of our atmosphere. The 2012 ball lightning incident in Russia provides a compelling case study illustrating the unpredictability of this phenomenon. Witnesses reported spherical luminous objects appearing during a thunderstorm, hovering for mere moments before vanishing. These orbs exhibited a variety of colors, ranging from white to blue, with distinct variations in size and luminosity, showcasing the complexity of their behavior. The region's atmospheric conditions were carefully monitored during this event. High humidity and electrical activity created an ideal backdrop for ball lightning formation. Measurements indicated significant fluctuations in electromagnetic fields, suggesting a potential correlation between these anomalies and the appearance of the luminous spheres. Localized weather systems played a vital role, as dense clouds and moisture provided the necessary environment for electrical charges to accumulate. Analyzing eyewitness accounts reveals a shared sense of wonder and confusion. Observers described the orbs floating, interacting with the surrounding environment. Some noted how they occasionally sparked or emitted a faint crackling sound. This sensory information enriches the understanding of ball lightning, adding layers to its elusive nature. Scientific inquiry into this incident remains ongoing, as researchers attempt to replicate the conditions that led to the formation of ball lightning. Each dataset gathered offers a glimpse into a phenomenon that continues to challenge existing scientific paradigms, blurring the lines between atmospheric science and unexplained occurrences. The effects of ball lightning on human health and safety remain elusive, with few documented cases providing a clear understanding of potential risks. Reports often describe individuals encountering these luminous spheres, sometimes resulting in varying outcomes. In instances where direct contact occurs, injuries range from minor burns to more severe trauma, raising concerns about the energy contained within such an anomaly. Witnesses frequently recount feelings of unease or disorientation in the presence of ball lightning, suggestive of its potential to disrupt the nervous system. This phenomenon can create a sense of confusion, even leading to temporary incapacitation. The unpredictable nature further complicates assessments of safety, as the occurrence can be transient and sporadic, eluding standard monitoring. The potential for ball lightning to ignite flammable materials introduces an additional layer of risk, particularly in environments where combustible substances are present. This aspect underscores the importance of understanding the interaction between atmospheric electricity and earthly matter. Investigations often indicate that these occurrences may be influenced by local weather conditions, suggesting a correlation between atmospheric phenomena and their effects on human safety. Continued study aims to unravel the complexities associated with these events, contributing to a broader understanding of atmospheric electricity. As research progresses, insights will be crucial for developing safety protocols. The difficulty in replicating ball lightning in laboratory conditions presents a significant challenge for scientists. Despite numerous attempts, recreating the elusive phenomenon in controlled environments has proven to be formidable. This region of atmospheric electricity exhibits unpredictable behavior, making it challenging to establish consistent parameters for experimentation. Many researchers have employed high-voltage discharges, seeking to mimic the conditions believed to contribute to its formation. Variations in temperature, pressure, and humidity further complicate these efforts, as they influence the behavior of electrical discharges within a given environment. The unique interplay between atmospheric conditions and electrical fields remains poorly understood, leading to an incomplete understanding of the mechanisms underlying ball lightning. Despite advanced technology, the transient nature of this phenomenon often eludes observation. The brief lifespan of ball lightning, typically lasting only a few seconds, hinders detailed analysis and measurement. Observational studies in natural settings provide valuable insights, yet the lack of reproducibility in laboratory settings leaves many questions unanswered. The quest for comprehension continues, with scientists exploring unconventional methods. Some experiments involve the use of plasmas and ionized gases, attempting to replicate the environmental conditions associated with ball lightning sightings. Each trial brings researchers closer to untangling the complexities of atmospheric electricity, fostering a deeper understanding of its enigmatic presence. Geographic patterns reveal intriguing insights into the phenomenon of ball lightning. Observations indicate a strong correlation with specific climatic regions, notably those with frequent thunderstorms. Areas such as the central United States, particularly the Great Plains, report higher occurrences, coinciding with intense electrical activity during convective storms. This region, characterized by vast open landscapes, provides optimal conditions for the formation and observation of such phenomena. Additionally, coastal zones where warm, humid air interacts with cooler maritime conditions also demonstrate a notable frequency. These interactions contribute to the development of unstable atmospheric conditions, further enhancing the likelihood of electrical events. Research indicates that certain high-altitude environments may serve as unique catalysts for ball lightning, potentially due to the interplay of atmospheric pressure and temperature gradients at elevation. Curiously, there are regions where these occurrences remain conspicuously absent. Deserts, for instance, tend to report fewer sightings, likely due to a lack of conducive moisture and electrical activity. These geographic variances prompt questions regarding the underlying mechanisms that govern the formation of ball lightning. Understanding these patterns not only aids in mapping its occurrences, but also assists in developing predictive models. Such insights could eventually enhance safety measures during electrical storms, minimizing risks associated with this elusive atmospheric phenomenon. Solar activity plays a significant role in the formation and behavior of ball lightning. This phenomenon is believed to be influenced by fluctuations in the solar wind, which carries charged particles from the sun toward Earth. During periods of heightened solar activity, such as solar flares or coronal mass ejections, the interaction between these charged particles and Earth's magnetic field can create conditions that may foster the development of ball lightning. The relationship between solar activity and atmospheric electricity is complex. Increased solar activity can lead to alterations in atmospheric pressure and temperature, which in turn affect local weather patterns. These changes might create conducive environments for electrical discharges, potentially resulting in the appearance of ball lightning. Specific atmospheric conditions, such as humidity and ionization levels, are essential for the formation of this unusual phenomenon. Research into the connection between solar phenomena and ball lightning is ongoing. Observations suggest that regions experiencing intense solar events may witness an uptick in reports of ball lightning sightings. Understanding these interactions could unravel the underlying mechanisms that govern ball lightning, offering insights into its occurrence and characteristics. Continued studies may illuminate how solar cycles influence atmospheric electricity, contributing to the broader comprehension of these enigmatic electrical occurrences. This intersection reveals a complex web of interactions between the Earth's atmosphere and its electrical phenomena. Researchers investigate the conditions under which ball lightning manifests, noting its tendency to appear during thunderstorms or in the vicinity of high-voltage power lines. Observations suggest that variations in humidity and temperature may play critical roles in its formation, creating a fertile ground for hypotheses surrounding atmospheric dynamics. This phenomenon often defies conventional understanding, presenting challenges in replicating its conditions in laboratory settings. As investigations proceed, scientists employ advanced imaging techniques to study its behavior, capturing fleeting appearances and movements. These observations, while limited in frequency, contribute valuable data to the growing repository of knowledge regarding transient luminous events. The presence of ball lightning in historical anecdotes serves as a backdrop for modern inquiries. Eyewitness accounts detail diverse manifestations from glowing orbs to elongated shapes, each offering clues to its underlying mechanics. These narratives blend with scientific analysis, fostering a richer dialogue between folklore and empirical research. With each discovery, the connection between atmospheric electricity and ball lightning becomes increasingly evident. Understanding these interactions may not only unravel the mysteries of ball lightning but also enhance broader atmospheric science, paving the way for insights into related phenomena such as sprites and elves, transient luminous events that also inhabit the realm of electrical activity within the atmosphere. Shifts in climate patterns introduce a nuanced interplay with atmospheric electricity, influencing the conditions under which ball lightning may manifest. Changes in temperature, humidity, and weather variability contribute to the development of thunderstorms, which in turn affect the occurrence of electrical discharges. In warmer climates, the increased energy in the atmosphere may lead to more frequent convective storms, potentially enhancing the likelihood of ball lightning occurrences. Alterations in surface temperatures influence the distribution of moisture, resulting in varied storm intensity and frequency. This region's evolving climatic conditions facilitate a landscape where electrical activity can thrive, suggesting a direct correlation between climate change and the dynamics of ball lightning. The rise in extreme weather events, including intense thunderstorms and unpredictable lightning, creates an environment ripe for the development of these enigmatic phenomena. Research into the frequency and characteristics of ball lightning in relation to climate change remains sparse. Observational data continue to be essential in identifying patterns and trends over time. Tracking these shifts may yield insights into how changes in the atmosphere affect electrical phenomena, providing a clearer understanding of the intricate relationship between climate and atmospheric electricity. As the climate continues to transform, the implications for ball lightning and similar events remain a critical area of inquiry within the scientific community. Research institutions play a pivotal role in advancing the understanding of ball lightning within their walls, and interdisciplinary teams converge, combining expertise from fields such as atmospheric science, electrical engineering, and physics. This collaborative environment fosters the development of innovative experimental techniques aimed at reproducing the elusive phenomena under controlled conditions. In his specialized laboratories, researchers employ high-voltage equipment to simulate the electrical discharges that may lead to the formation of ball lightning. Through these experiments, data is meticulously collected, providing insights into the conditions that may favor its emergence. Observations of natural ball lightning also generate valuable information. Field studies conducted during thunderstorms capture the fleeting moments of these events, allowing scientists to analyze their characteristics and behaviors. Theoretical models are equally important, as they attempt to explain the mechanisms underlying ball lightning formation. Simulations run on advanced computing systems help visualize potential scenarios, guiding empirical investigations and refining hypotheses. Peer-reviewed publications emerge from these institutions, disseminating findings to the wider scientific community and sparking further dialogue. Outreach programs extend this knowledge beyond academic circles, educating the public on atmospheric phenomena while fostering an appreciation for the complexities of natural electricity. As research continues, the collaborative efforts of these institutions may eventually unravel the mysteries surrounding ball lightning, contributing to a broader understanding of atmospheric electricity. The intricate relationship between ball lightning and other electric phenomena reveals a fascinating aspect of atmospheric science. Instances of lightning strikes, particularly cloud-to-ground discharges, share commonalities with ball lightning, suggesting underlying mechanisms that require further exploration. Observations indicate that this form of lightning can occur alongside traditional lightning events, often in close proximity. The characteristics of these occurrences, including duration and luminosity, provoke questions about their formation processes. In addition, the role of thunderstorms as a backdrop for both phenomena enhances their connection. The charged environments created during these storms lead to an array of electrical activities, from forked lightning to the elusive sphere. Researchers have noted that ball lightning frequently appears during or after thunderstorms, hinting at a possible relationship to the electrical discharges that define such weather systems. Comparative studies involving sprite lightning, another enigmatic form of atmospheric electricity, further deepen the inquiry. Like ball lightning, sprites manifest above thunderstorm clouds, revealing a complex interplay of electrical charges in the atmosphere. Understanding these relationships may unlock new insights into the formation and behavior of ball lightning, inviting the investigation into ball lightning's connection with other electric phenomena underscores the importance of interdisciplinary research, blending meteorology, physics, and atmospheric chemistry, as scientists strive to illuminate the nature of these captivating events. Social media platforms have become vital in documenting and disseminating ball lightning sightings, offering a unique lens through which these elusive phenomena can be analyzed. Users share images and videos that may provide crucial evidence, while eyewitness accounts contribute to a growing database of reported occurrences. This collective effort assists researchers in identifying patterns and characteristics associated with ball lightning. The immediacy of social media facilitates real-time reporting, enabling individuals to communicate their experiences as they unfold. Geographic tagging allows for the mapping of sightings, revealing potential clusters or specific regions where these events are more prevalent. Analysis of such data can guide future scientific inquiries, focusing on the atmospheric conditions present during reported incidents. Engagement within online communities fosters discussions that bridge the gap between amateur enthusiasts and professional scientists. This interaction encourages the sharing of theories and hypotheses, often leading to innovative approaches to studying atmospheric electricity. While the scientific community approaches these reports with caution, acknowledging the potential for misinformation, the aggregated user-generated content presents an opportunity for increased awareness and inquiry. Vaulted by contextualizing ball lightning within a broader framework of atmospheric phenomena, social media serves as both a repository of knowledge and a catalyst for exploration. The intersection of technology and natural science continues to evolve, shaping how these captivating events are understood. At first, skepticism permeates the scientific community regarding claims of ball lightning. Reports often emerge from eyewitness accounts, filled with intrigue yet lacking empirical validation. Those in the field scrutinize the anecdotal nature of these observations, seeking reproducibility in controlled environments. This skepticism is not merely a dismissal, it reflects a rigorous commitment to the scientific method. Research efforts have intensified, with laboratories attempting to replicate the phenomenon under various conditions, including high-voltage experiments and plasma studies. These investigations aim to uncover whether ball lightning can be generated artificially and whether its properties align with existing theories of atmospheric electricity. Numerous hypotheses emerge, ranging from the behavior of ionized gases to complex interactions between electromagnetic fields and physical matter. Each theory faces challenges in providing a comprehensive explanation for the phenomenon's unpredictable nature and varied appearances. Some researchers propose that ball lightning may serve as a manifestation of atmospheric electricity that remains poorly understood. Collaborations among physicists, meteorologists, and electrical engineers illustrate the interdisciplinary approach taken to dissect these enigmatic occurrences. This growing body of work reflects a shared curiosity and a collective drive to unravel the complexities of ball lightning, fostering a deeper understanding of atmospheric phenomena. The pursuit remains ongoing, with each study contributing incrementally to the knowledge surrounding this elusive phenomenon. Preopiquetia unis agon ha contabrescent a significant challenge in documenting ball lightning. Descriptions can vary widely, influenced by individual perceptions and environmental conditions. These accounts typically showcase a range of shapes, colors, and behaviors, complicating the task of establishing a consistent scientific framework. In many cases, witnesses report the phenomenon appearing suddenly, hovering, or darting unpredictably before vanishing, leaving behind a lingering sense of wonder and confusion. Scientific evidence remains scarce, primarily due to the transient nature of the phenomenon. Observations are typically fleeting, with events lasting mere seconds, which makes it difficult for instruments to capture reliable data. While advances in technology have improved the capability to record atmospheric events, the unpredictable occurrence of ball lightning often eludes detection, limiting comprehensive analysis. Controlled laboratory experiments have attempted to replicate conditions that might lead to ball lightning, but have yet to yield consistent results. The phenomena's elusive properties challenge researchers to create reliable hypotheses. This region of atmospheric study requires a delicate balance between anecdotal evidence and empirical research. The gap between subjective experiences and objective measurements continues to fuel the mystery, prompting scientists to explore innovative approaches to understanding the underlying mechanisms of this enigmatic atmospheric occurrence. Each investigation builds upon previous findings, gradually illuminating the complexities of ball lightning. Emerging from the shadows of uncertainty, theoretical frameworks provide a structured approach to understanding ball lightning. These models aim to reconcile the disparate observations that characterize this phenomenon. One prominent theory proposes that it arises from the ionization of air, creating a stable plasma state. This energetic state, enriched with charged particles, may account for the luminous appearance and erratic behavior commonly reported. Further exploration suggests that ball lightning could be a manifestation of electromagnetic fields interacting with atmospheric conditions. The interplay of these forces may trap energy within a localized region, giving rise to the glowing orbs. Observations of ball lightning often indicate a correlation with thunderstorms, suggesting that strong electrical activity may catalyze the formation of these entities. Numerous simulations have been conducted to replicate the conditions under which ball lightning occurs. These experiments often reveal that varying humidity, temperature gradients, and wind patterns contribute to its stability. Theories also point to the possibility of chemical reactions occurring within the sphere, leading to the distinctive colors and movement patterns witnessed by observers. Research continues to expand the theoretical landscape, incorporating insights from quantum mechanics and thermodynamics. Understanding the nature of ball lightning remains an interdisciplinary endeavor, drawing from atmospheric science, electromagnetism, and materials science to piece together this enigmatic phenomenon. The journey toward clarity persists, revealing the intricate mechanics underlying atmospheric electricity. Particle physics plays a crucial role in unraveling the complexities of ball lightning. Within this enigmatic phenomenon, interactions among charged particles are believed to create the conditions necessary for its existence. Electrons and ions, under specific circumstances, can become trapped within a localized region of space, leading to a sustained luminous entity. This process is influenced by the surrounding electromagnetic fields, which shape the behavior of these particles. Research indicates that the energy density within these regions can reach astonishing levels. When the right balance of atmospheric conditions occurs, the energy released can manifest as the luminous sphere commonly associated with ball lightning. Such high-energy environments can produce exotic particles that may contribute to the stability of these formations. The theoretical models often explore the possibility of quantum tunneling, allowing particles to transition through barriers that would typically confine them. This phenomenon could explain the seemingly erratic movements observed in ball lightning as it navigates through varying densities of air. Observations suggest that these entities may exhibit behaviors reminiscent of plasma, further linking them to the principles of particle physics. Understanding the intricate interplay of forces at the quantum level enhances the comprehension of this atmospheric mystery. Each advancement in particle physics brings researchers closer to constructing a cohesive narrative surrounding the elusive nature of ball lightning. Ball lightning manifests as luminous spheres, often observed during thunderstorms, defying conventional explanations of atmospheric electricity. Sightings describe these orbs drifting silently, at times interacting with their surroundings in ways that challenge established scientific understanding. Some witnesses report the phenomena hovering near structures, illuminating the environment with a soft glow, while others note their sudden disappearance, leaving behind a lingering aura of mystery. The relationship between ball lightning and unidentified flying objects has intrigued many people. Eyewitness accounts occasionally blur the lines between these atmospheric phenomena and extraterrestrial craft. The appearance of a glowing sphere, coupled with inexplicable movement patterns, creates a fertile ground for speculation. Researchers have noted that both phenomena share certain characteristics, such as unpredictability and an unusual visual presence, leading to theories suggesting a possible connection. Scientific investigations into ball lightning have resulted in various hypotheses, ranging from the behavior of ionized gases to complex electromagnetic interactions. Understanding these mechanisms may shed light on why these luminous spheres are sometimes mistaken for UFOs. Despite rigorous experimentation, the mystery remains largely unresolved. Current studies employ advanced imaging technologies and sensor networks to capture instances of ball lightning. These efforts aim to demystify its origins and behavior. Each observation contributes to a growing database, offering hope that the enigma of ball lightning may one day find a definitive explanation within the broader context of atmospheric science. Theories surrounding ball lightning have undergone significant evolution over the centuries. Initial descriptions date back to ancient times, where it was often interpreted as a divine phenomenon or an omen. These early accounts lacked scientific grounding, relying instead on folklore and superstition. As the scientific method gained prominence in the 17th and 18th centuries, more systematic observations emerged. Scholars began documenting unexplainable luminous spheres occurring during thunderstorms. In the 19th century, the phenomenon began to attract the attention of physicists who sought to understand its characteristics. Various hypotheses were proposed, ranging from electrified atmospheric particles to chemical reactions involving natural gases. Yet, each explanation fell short of providing a comprehensive model. This period marked a shift toward a more empirical approach, as researchers meticulously recorded instances and attempted to replicate the conditions under which ball lightning appeared. The 20th century heralded advancements in technology that allowed for more rigorous experimentation. High-speed photography and electrical measurements provided new insights, yet the elusive nature of the phenomenon continued to frustrate scientists. Contemporary theories now explore the intersection of plasma physics and electromagnetic fields, suggesting that it may involve complex interactions of electrons and ions within localized environments. This ongoing inquiry reflects the dynamic interplay between observation and theory that characterizes the study of atmospheric electricity. The quest for understanding remains a fundamental aspect of this captivating field. Folklore has long shaped perceptions of atmospheric phenomena, with ball lightning serving as a prime example. Tales of glowing orbs appearing during thunderstorms have permeated cultures worldwide, often described as the souls of the departed or omens of misfortune. These narratives reflect humanity's attempts to make sense of unpredictable natural events. Such stories can sometimes obscure the scientific inquiry, leading to a blend of myth and reality that complicates understanding. In many regions, traditional accounts recount the sudden emergence of these luminous spheres, often associated with intense electrical activity. These descriptions frequently align with actual observations, suggesting a cultural resonance that bridges legend and empirical evidence. The interplay between these narratives and scientific investigation illustrates how folklore can shape expectations and interpretations of natural occurrences. Encounters with ball lightning frequently evoke sensations of awe and fear, reinforcing the mysterious allure of this phenomenon. Reports often detail the unpredictable behavior of these orbs, moving through spaces in seemingly sentient ways, further entrenching their enigmatic status within folk traditions. This intersection of myth and science serves as a reminder of the complexities involved in unraveling atmospheric mysteries. Understanding ball lightning requires acknowledging both the cultural contexts that have shaped its interpretation and the ongoing scientific efforts aimed at demystifying its nature. Each narrative enriches the broader conversation surrounding atmospheric electricity, contributing to a deeper comprehension of its elusive characteristics. The 1960s marked a pivotal era in the exploration of ball lightning, particularly within the United States. Observations during this decade offered a unique glimpse into its unpredictable nature. Numerous reports emerged from various states, detailing encounters with luminous spheres drifting through the air. Witnesses described these phenomena as ranging in size from a few centimeters to several meters in diameter, often displaying a variety of colors, including white, yellow, and blue. Certain accounts indicated that it would hover silently, occasionally darting about with remarkable agility. These orbs seemed to interact with their surroundings, sometimes igniting flammable materials or producing a faint hissing sound. Reports often noted their sudden disappearance, leaving behind no trace or explanation. The scientific community grappled with these accounts, striving to reconcile them with existing knowledge of atmospheric phenomena. Research efforts intensified, leading to controlled experiments aimed at replicating the conditions under which ball lightning might occur. Despite numerous attempts, a definitive understanding remained elusive. Investigations revealed that these occurrences typically coincided with thunderstorms, suggesting a connection between ball lightning and intense electrical activity in the atmosphere. While many theories emerged, including those relating to plasmas and chemical reactions, none provided a comprehensive explanation. The mystery of ball lightning continued to intrigue researchers, prompting ongoing studies into its enigmatic nature. Computer simulations have emerged as a pivotal tool in the exploration of ball lightning phenomena. These intricate models allow scientists to recreate the complex interactions between charged particles and the surrounding environment by manipulating variables such as humidity, temperature, and electromagnetic fields. Researchers simulate conditions under which ball lightning might occur. This region of inquiry benefits significantly from advancements in computational power. High-resolution simulations can capture the dynamic behavior of plasma, providing insights into how energy is concentrated and released in these mysterious orbs. Observational data from rare sightings serve as a reference point, guiding the development of these virtual experiments. In addition to creating models of ball lightning formation, simulations explore various hypotheses regarding its life cycle. They evaluate potential mechanisms, such as the role of microwaves or chemical reactions in sustaining these luminous entities. By predicting behaviors and characteristics, scientists test theories that have eluded conventional experimentation. Collaboration among researchers enhances the effectiveness of these simulations, allowing diverse expertise to converge on this elusive subject. Results from computational studies contribute to a growing body of knowledge, generating discussions about the implications for atmospheric physics. This collective effort aims to demystify a phenomenon that has long captivated the scientific community, inching closer to a comprehensive understanding of its nature. Standing questions persist regarding the mechanisms behind ball lightning formation. Observations indicate that these luminous spheres can appear during thunderstorms, yet their specific origins remain elusive. Reports describe them as floating orbs, sometimes hovering or darting erratically, which complicates the effort to ascertain their physical properties. The duration of these phenomena is another area of intrigue. While some instances last mere seconds, others claim sightings that extend for several minutes. Such variability raises questions about the processes sustaining their existence. Researchers speculate about the role of atmospheric conditions, yet a definitive connection has yet to be established. The composition of ball lightning adds another layer of complexity. Some hypotheses suggest that these entities could be composed of ionized gases or electromagnetic fields, while others propose interactions with nanoparticles. These competing theories reflect the ongoing struggle to consolidate observations into a unified model. Witness accounts frequently describe their striking visual qualities, yet the lack of consistent documentation poses challenges for verification. Recorded instances remain sporadic and often anecdotal, making it difficult to conduct systematic studies. This enigmatic phenomenon continues to elude precise characterization, leading to a growing compendium of hypotheses. Each potential explanation invites further inquiry, revealing the intricate relationship between atmospheric electricity and human understanding of natural phenomena. An interdisciplinary collaboration plays a crucial role in advancing the study of ball lightning. Physicists, meteorologists, and electrical engineers unite their expertise to probe this elusive phenomenon. This partnership generates a wealth of knowledge, combining theoretical frameworks with practical observations. Laboratory experiments conducted under controlled conditions allow researchers to simulate some aspects of ball lightning, while field studies capture its unpredictable nature within the atmosphere. Mathematicians contribute by developing models that seek to explain the formation and behavior of these luminous spheres. Their equations provide insight into the potential mechanisms behind the phenomena, offering a theoretical foundation upon which empirical data can be scrutinized. Insights from materials science inform researchers about the potential interactions between ball lightning and various surfaces. including conductive and non-conductive materials. The history of these studies highlights the importance of sharing knowledge across disciplines. Each new discovery prompts questions that existing frameworks may not address, necessitating collaboration with experts from other fields. This dynamic exchange fosters innovation, paving the way for new technologies and improved safety measures in environments where ball lightning might occur. Each perspective enriches the understanding of atmospheric electricity, reinforcing the notion that complex scientific mysteries often require collective expertise to unravel. This synergy not only enhances comprehension, but also propels the entire field of atmospheric science forward. Educational institutions play a pivotal role in unraveling the complexities surrounding ball lightning. Through structured programs, students and researchers alike are introduced to the intricate phenomena of atmospheric electricity. Courses in atmospheric science emphasize the importance of empirical data and theoretical frameworks, fostering a new generation of scientists equipped to explore these enigmatic occurrences. Dedicated research initiatives encourage collaborative projects, allowing for the pooling of diverse expertise and resources. Public outreach initiatives serve to bridge the gap between scientific communities and the general populace. Informative lectures and community workshops raise awareness of ball lightning, demystifying its elusive nature. This engagement cultivates curiosity and interest, inviting individuals to consider the scientific explanations behind such phenomena. As a result, a more informed society begins to appreciate the nuances of atmospheric events. In addition, advancements in technology facilitate the study of these phenomena. High-resolution imaging and real-time data collection provide unprecedented insights. Educational platforms can harness these tools to create interactive learning experiences, enabling deeper understanding of ball lightning's characteristics. The ongoing dialogue between academia and the public nurtures a culture of inquiry. As knowledge spreads, it lays the groundwork for future discoveries. Each new insight contributes to a collective understanding, inching closer to solving the mystery of ball lightning while illuminating the broader realm of atmospheric electricity. Emerging technologies are poised to reshape the landscape of ball lightning research. Advanced observational techniques, including high-speed cameras and sophisticated electromagnetic sensors, facilitate the capture of transient phenomena with unprecedented clarity. These tools enhance the ability to document elusive manifestations, shedding light on the conditions under which they occur. Collaboration between atmospheric scientists and physicists fosters a multidisciplinary approach, combining insights from both fields to unravel the complexities of electrical discharges. Computational modeling has also advanced, allowing researchers to simulate the intricate dynamics of ball lightning formation and behavior. Utilizing high-performance computing resources, these simulations provide a virtual laboratory for testing hypotheses that would be difficult to replicate in natural settings. Field studies are being augmented by drones equipped with specialized sensors that can traverse storm systems in real time. This method offers a unique vantage point, capturing data from previously inaccessible atmospheric layers. The incorporation of artificial intelligence into data analysis streamlines the identification of patterns, enabling researchers to sift through vast datasets more efficiently. The potential for breakthroughs lies in the integration of these technologies, creating a comprehensive framework for studying ball lightning. As insights accumulate, they promise to bridge the gap between observed phenomena and theoretical understanding, paving the way for a deeper comprehension of this enigmatic aspect of atmospheric electricity. Research into ball lightning may yield transformative applications, especially in the realms of technology and energy. Understanding the mechanisms behind this phenomenon can inspire the development of new energy storage systems. These systems could harness the unique properties exhibited by ball lightning, potentially leading to innovations in battery technology that emphasize efficiency and longevity. Advancements may extend to telecommunications as well. The electromagnetic properties associated with ball lightning could inform the design of novel communication devices. Enhanced signal transmission methods might emerge, utilizing principles derived from the behavior of these luminous spheres during extreme weather events. Materials science stands to benefit as well, particularly through the exploration of plasma states and their interactions. Insights from ball lightning could guide the creation of novel materials with unique electrical and thermal properties. These developments may lead to more efficient conductors or insulators, benefiting various industries from electronics to energy production. Additionally, safety protocols in storm-prone areas might be informed by a deeper understanding of ball lightning. Predictive models could emerge, enabling better preparedness against electrical hazards during severe weather conditions. In this quiet pursuit of knowledge, the implications of ball lightning research unfold, guiding humanity toward practical applications that intertwine with the very fabric of our technological future. Atmospheric scientists play a crucial role in unraveling the enigmatic nature of ball lightning. Their meticulous observations and experiments contribute to a deeper understanding of this phenomenon, which remains elusive despite centuries of inquiry. These researchers utilize advanced instrumentation to monitor atmospheric conditions, capturing data on temperature, humidity, and electric fields. Such analyses are essential for identifying the specific environments in which ball lightning occurs. Field studies often involve deploying equipment in locations with a history of sightings. This region becomes a living laboratory authority, where scientists observe the behavior of electrical discharges during thunderstorms. Instruments measure variations in electromagnetic fields, while high-speed cameras document fleeting appearances. The transient nature of ball lightning demands precision and persistence, as researchers must remain vigilant, ready to document rare events under unpredictable circumstances. Collaborative efforts among scientists also facilitate a broader understanding of the phenomenon. By sharing findings and refining hypotheses, they strengthen the theoretical framework surrounding atmospheric electricity. The integration of interdisciplinary approaches, encompassing physics, chemistry, and meteorology, enhances the quest for answers. Ball lightning represents not just a scientific challenge, but also a testament to the wonders of natural phenomena. As atmospheric scientists continue their investigations, each revelation contributes to a greater comprehension of the complex interactions within our atmosphere, paving the way for future breakthroughs. Investigating ball lightning necessitates careful ethical considerations, particularly concerning public safety. This phenomenon, characterized by its unpredictable nature, raises significant questions regarding the risks associated with studying it. Researchers must navigate the delicate balance between advancing scientific knowledge and ensuring the well-being of individuals who may inadvertently encounter such discharges. Field research often involves outdoor settings where electrical phenomena can occur spontaneously. This unpredictability necessitates stringent safety protocols, including distance regulations and protective equipment for researchers. Observational studies, while informative, pose risks to both the observers and nearby populations, particularly in areas prone to thunderstorms. Effective communication with the public is essential to mitigate fears surrounding ball lightning. Many individuals may not understand the scientific basis of the phenomenon, leading to misconceptions that could exacerbate anxiety. Transparency in research findings fosters trust, allowing communities to feel informed rather than alarmed. Regulatory frameworks must also evolve to encompass the unique nature of this atmospheric event. Establishing guidelines that prioritize safety while facilitating research opportunities is crucial. Collaboration with meteorological organizations can enhance understanding and provide vital data that aids in developing effective safety measures. Through responsible research practices, the scientific community strives to unravel the mysteries of ball lightning while safeguarding public welfare. A commitment to ethical standards will foster an environment conducive to sharing knowledge across borders. Collaboration among researchers from diverse backgrounds enhances the understanding of ball lightning, an atmospheric phenomenon that eludes definitive explanation. Scientists from various countries bring unique methodologies and perspectives, creating a rich reservoir of data to analyze. These partnerships enable the pooling of resources, leading to more comprehensive field studies. Researchers in remote areas where ball lightning occurrences are reported can utilize advanced observational equipment, furthering the understanding of this elusive phenomenon. Workshops and conferences facilitate the exchange of ideas, allowing scientists to discuss findings and refine hypotheses. Access to a global network accelerates the pace of discovery. Joint research projects often lead to breakthroughs that would be difficult to achieve in isolation. The accumulation of case studies over time contributes to a clearer picture of ball lightning's characteristics and behavior. The enigmatic nature of this phenomenon invites continuous inquiry. Different atmospheric conditions, geographic locations, and cultural interpretations enrich the investigation. This collaboration does not only focus on the physical properties of ball lightning, but also addresses its potential implications for safety and energy. Each new piece of information builds a foundation upon which future research can be constructed, inching closer to unraveling the complexities of ball lightning. Interest in this phenomenon extends beyond the realms of science, permeating popular culture and media. It appears in literature, film, and folklore, often depicted as an ethereal or supernatural occurrence. Stories recount eerie encounters with glowing spheres, imbuing them with a sense of mystery and wonder. These narratives serve not only to captivate the imagination, but also to reflect humanity's quest to understand the unknown aspects of nature. Mihu Eindview on the Bullshow. In Fulls, numerous authors have woven ball lightning into their plots, exploring themes of chaos and the sublime. These tales often juxtapose scientific inquiry with the fantastical, illustrating how the phenomenon bridges the gap between empirical observation and myth. Films have similarly portrayed it as an enigmatic force, inviting viewers to ponder its origins and implications. These portrayals, while fictionalized, raise awareness of atmospheric phenomena and their potential to inspire curiosity. Through documentaries and educational programs, discussions surrounding ball lightning continue to flourish, inviting experts to share insights and theories. This dialogue fosters a broader appreciation for the complexities of atmospheric electricity. In folklore, regional legends often attribute supernatural qualities to these phenomena, revealing cultural interpretations that align with historical experiences of natural events. Such representations reinforce the enigmatic nature of ball lightning, ensuring its place in both scientific inquiry and the collective human psyche. Pioneering studies have emerged from the minds of key scientists dedicated to unraveling the complexities of ball lightning. These individuals have approached the phenomenon from diverse angles, employing experimental, observational, and theoretical frameworks. One notable figure, Thomas Townsend Brown, conducted experiments in the mid-20th century that hinted at the role of electric fields in the formation of these luminous orbs. His work suggested that ball lightning might be related to the behavior of charged particles under certain conditions. Subsequent research by scientists like John Abrahamson further advanced the understanding of this atmospheric enigma. He proposed that ball lightning could be a manifestation of plasma, a state of matter formed under high energy conditions. This theory gained traction, prompting further investigation into the energy sources needed for such phenomena. The contributions of these researchers underscore a gradual accumulation of knowledge, although definitive conclusions remain elusive. The elusive nature of these luminous spheres has also drawn the attention of physicists such as David H. Smith, who explored the possibility of microwave emissions being involved in their creation. Observational accounts continue to fuel interest, with each sighting providing a potential clue. This ongoing dialogue among scientists reflects a shared pursuit of understanding a phenomenon that continues to challenge established scientific paradigms. The influence of climate variability introduces complex dynamics to the occurrence of ball lightning. Changes in atmospheric conditions, such as temperature fluctuations and humidity levels, can alter electrical discharge processes. This region experiences a delicate balance between moisture and thermal energy, creating environments ripe for electrical phenomena. Research indicates that increased atmospheric instability, often linked to climate change, may enhance the conditions conducive to ball lightning formation. Elevated temperatures can lead to more vigorous thunderstorms, fostering environments where unusual electrical activity is more likely to manifest. These occurrences are not uniformly distributed. Certain geographical areas may experience a higher frequency of ball lightning as climatic conditions shift. The interactions between rising sea temperatures and atmospheric pressure systems promote unpredictable weather patterns. They contribute to the generation of intense electrical storms, which may increase the probability of ball lightning events. Observations suggest that regions with a history of electrical storms often report sightings of this enigmatic phenomenon during or after extreme weather events. Understanding the relationship between climate variability and ball lightning not only provides insights into the mechanisms behind its formation, but also emphasizes the broader implications of a changing climate on atmospheric electricity. This line of inquiry continues to unfold, revealing the intricate connections between our planet's climate systems and the mysteries of electrical phenomena. Understanding these phenomena may significantly enhance natural disaster preparedness. Insights gained from ball lightning research could inform the development of more effective warning systems for severe weather events. This region, often marked by unpredictable electrical activities, presents a unique challenge for meteorologists and emergency responders. Anomalous electrical discharges like ball lightning may serve as indicators of impending storms, suggesting that further study could yield vital data for disaster forecasting. Exploring the properties of this atmospheric phenomenon adds layers to our comprehension of lightning's behavior during extreme weather. It is theorized that variations in electrical activity can influence storm intensity and longevity. This correlation may eventually allow scientists to refine predictive models, potentially providing earlier warnings to communities in harm's way. In addition to forecasting, understanding the mechanisms of ball lightning could lead to advancements in technology designed to mitigate the effects of severe electrical storms. Innovations in grounding techniques and building materials could emerge from a deeper grasp of how electrical forces interact with the atmosphere. This necessitates interdisciplinary collaboration between atmospheric scientists, engineers, and disaster management professionals. The implications of this research extend beyond mere academic interest. They touch upon the very essence of safeguarding lives and infrastructure in the face of increasingly volatile climate patterns. Such advancements have the potential to transform our approach to resilience in an uncertain world. The role of citizen science in documenting ball lightning observations has gained increasing significance. Enthusiasts and amateur scientists contribute valuable data by capturing instances of this phenomenon through photographs and videos. With the advent of social media and dedicated forums, these individuals share experiences that were once obscure, allowing a broader community to analyze and interpret phenomena that often elude traditional scientific inquiry. The irregularity and rarity of ball lightning events present challenges for researchers. Each account, whether documented through a smartphone or recorded in a personal journal, adds pieces to a complex puzzle. Observations made across diverse geographical regions contribute to a more comprehensive understanding of environmental conditions that may influence the formation of these luminous spheres. Patterns emerge from collective data, revealing correlations with weather conditions, topography, and even human activity. This grassroots effort empowers individuals to engage with science actively, bridging the gap between experts and the general public. The enthusiasm surrounding these contributions fosters an atmosphere of shared curiosity, where questions lead to collaborative exploration. Through these efforts, the documentation of ball lightning evolves into a communal pursuit of knowledge. Each shared story not only enriches scientific understanding, but also highlights the intricate relationship between humanity and the atmospheric phenomena that envelop our world. The potential for ball lightning to inform energy generation technologies represents a fascinating intersection of atmospheric science and innovation. This enigmatic phenomenon has been observed in various conditions, often appearing as luminous spheres that drift through the air, seemingly defying conventional understanding of electricity and plasma. Its elusive nature raises questions about the underlying mechanisms that allow it to form and persist, offering insights into energy dynamics that remain largely unexplored. Researchers are beginning to draw parallels between the characteristics of ball lightning and advanced energy generation methods. The unique properties of this atmospheric anomaly, such as its ability to exist in a stable form for brief periods, suggest that it may provide critical clues for harnessing energy more effectively. For instance, the principles governing its formation and stability could inspire new designs for energy storage or transmission systems. In this context, studying ball lightning may lead to innovative applications in renewable energy technologies. Understanding how it interacts with the environment could pave the way for improved efficiency in solar panels or wind turbines. The knowledge gained from these investigations may contribute to the development of systems that tap into atmospheric electricity, thus promoting sustainable energy solutions. Each revelation about ball lightning carries the potential to reshape our approach to energy in a world increasingly reliant on renewable resources. The interaction between ball lightning and biological systems presents an intriguing area of study. Observations indicate that this phenomenon can have profound effects on living organisms. Encounters with ball lightning have been reported to induce a range of reactions, from temporary paralysis to heightened electrical sensitivity in individuals. These responses suggest that the energy emitted by these luminous orbs might interact with biological tissues in ways not fully understood. Investigating this interaction reveals the potential for ball lightning to impact cellular structures. The high-energy fields associated with these entities could influence ion channels within cells, leading to significant physiological changes. These effects may vary based on the intensity and duration of exposure of Unsolved at an Unsolved, making it difficult to generalize findings across different biological systems. Cases of injuries sustained during ball lightning events have been documented, including burns and neurological disturbances that last long after the phenomenon has dissipated. Such outcomes necessitate a thorough examination of the underlying mechanisms at play. Understanding how this atmospheric electricity interacts with biological systems could illuminate not only the properties of ball lightning itself, but also broader principles of electrical phenomena in nature. Research continues into the potential applications of this knowledge, including the development of advanced technologies that harness aspects of this enigmatic force, further bridging the gap between atmospheric science and biology. Theoretical physics plays a crucial role in unraveling the complexities of ball lightning phenomena. Various models have been proposed to explain the formation and behavior of these luminous orbs. Quantum mechanics, for instance, provides insights into the interactions of particles at a subatomic level, which may contribute to the stability of ball lightning. Electromagnetic theories also offer explanations regarding the generation of the intense electric fields that could create these transient entities. Mathematical simulations based on electromagnetic principles help visualize the conditions under which ball lightning can form. These simulations often include variables such as atmospheric pressure, humidity, and temperature fluctuations, creating a comprehensive map of ideal conditions. Researchers also explore how turbulence within the atmosphere may influence the trajectory and lifespan of these phenomena. Studies suggest that the energy required for ball lightning to manifest could stem from the surrounding environment, potentially drawing from the electric fields created during thunderstorms. The interplay between charged particles and their environment becomes significant, and understanding this relationship could lead to breakthroughs in energy storage and transfer systems. Theoretical investigations continue to evolve alongside experimental findings, pushing the boundaries of what is known about this atmospheric enigma. As data accumulates, the potential for a unified theory of ball lightning becomes increasingly plausible, linking diverse fields of study in an effort to decode this enduring mystery. Field studies play a crucial role in unraveling the complexities surrounding ball lightning. Observations made in situ provide invaluable insights that laboratory experiments often cannot replicate. These natural phenomena, appearing unpredictably in various environments, challenge researchers to capture and analyze their intricate behaviors under real-world conditions. Each encounter reveals unique characteristics, from their size and color to their movement patterns and interactions with the surrounding atmosphere. As scientists venture into storm-prone regions, they seek to document these occurrences with precision. Instruments capable of measuring electromagnetic fields, atmospheric pressure, and temperature fluctuations are deployed, allowing for a comprehensive analysis of these elusive entities. The data collected during these expeditions contribute to a growing database that sheds light on the conditions under which ball lightning manifests. Patterns emerge, occultly, suggesting correlations with specific meteorological phenomena. For instance, instances of ball lightning seem more prevalent during thunderstorms, aligning with increased electrical activity in the atmosphere. This correlation enhances the understanding of the interplay between atmospheric electricity and the formation of such anomalies. By isolating these events in their natural context, researchers aim to discern underlying mechanisms that govern their existence. The findings from field studies lay the groundwork for developing theories that could eventually bridge gaps between physics, atmospheric science, and electrical engineering, illuminating the enigmatic nature of ball lightning. This enigmatic phenomenon has been linked to global electrical activity in the atmosphere, demonstrating a complex interplay of forces. Observations suggest that regions experiencing heightened electrical activity may be more susceptible to ball lightning occurrences. Lightning strikes generate powerful electromagnetic fields that can influence the surrounding environment, leading to conditions favorable for the formation of these elusive orbs. Research indicates that ball lightning may arise from the interaction between charged particles and the surrounding air, creating a unique environment ripe for electrical phenomena. In this context, the presence of thunderstorms plays a critical role. These storms act as natural laboratories, generating various electrical discharges and disturbances. Such environments harbor the potential for ball lightning to manifest, often in the aftermath of lightning strikes. The spatial distribution of ball lightning reports aligns with areas of frequent electrical discharges, suggesting that atmospheric conditions conducive to lightning may also nurture the formation of these glowing spheres. This correlation invites further investigation into the mechanisms at play. Understanding the nuances of this connection could unlock insights into the broader implications of electrical behavior in the atmosphere. Research continues to explore how these phenomena interact with each other, potentially revealing new dimensions of atmospheric electricity. The quest for knowledge remains vital in demystifying the connections that bind these occurrences together within the fabric of our planet's electrical landscape. Weather patterns significantly influence the conditions under which ball lightning manifests. Specific atmospheric configurations, such as thunderstorms, create a fertile ground for these enigmatic phenomena. The interplay of warm, moist air at surface levels rising into cooler, drier regions above can generate unstable atmospheric conditions. This instability often leads to the formation of cumulonimbus clouds, which serve as the breeding ground for electrical activity. Within these towering giants, the intricate dynamics of updrafts and downdrafts contribute to the generation of electric fields. It is within this charged environment that ball lightning may emerge, drifting through the air with an elusive grace. The ionization caused by lightning strikes, combined with the moisture content in the surrounding air, may play a crucial role in the creation of these luminous spheres. Observations indicate that ball lightning frequently occurs during or immediately following thunderstorms, suggesting a correlation with the electrical discharges that characterize these weather events. As researchers study the conditions surrounding ball lightning appearances, the potential connections to other atmospheric phenomena are examined. The relationship between temperature gradients, humidity fluctuations, and electrical fields remains an area of focused inquiry. Understanding these links could illuminate the mechanisms underpinning the formation and behavior of this captivating atmospheric anomaly, paving the way for future discoveries in atmospheric science. Investigating the microphysical processes of ball lightning reveals a complex interplay of atmospheric conditions and energetic phenomena. These luminous spheres, often appearing during thunderstorms, challenge conventional explanations of electrical discharge. Observations indicate that they may arise from a combination of ionized particles and plasma formations, leading to their distinctive glow and erratic movement. Research suggests that the formation of ball lightning could be linked to specific environmental variables. High humidity, temperature fluctuations, and certain atmospheric pressure conditions may contribute to the development of these entities. It is within the intricate balance of these factors that the precise mechanisms may be nestled, waiting to be unraveled by meticulous study. Detailed analysis of the spectral emissions from ball lightning provides insight into its chemical composition. The presence of various elements, such as silicon, suggests interactions with the surrounding environment that could yield valuable information about the conditions necessary for its existence. Observations of its behavior, including its tendency to hover or move along surfaces, further complicate the understanding of its physical properties. Field studies, although fraught with challenges, have yielded anecdotal evidence of ball lightning's behavior. These observations point toward phenomena that defy expectations, often disappearing without a trace. Each incident contributes to a growing database, essential for piecing together the elusive nature of this atmospheric curiosity. Understanding these processes may illuminate the complex relationship between urban environments and atmospheric phenomena. Urbanization introduces a multitude of variables that can influence the occurrence and characteristics of ball lightning. The abundance of electrical infrastructure within cities creates a unique electromagnetic landscape. The presence of numerous high-rise buildings alters local wind patterns, affecting the distribution of charged particles in the atmosphere. This region, densely populated and filled with metal structures, may serve as a catalyst for the formation of ball lightning. The interactions between different materials and atmospheric electricity can generate conditions favorable to its emergence. Elevated temperatures and humidity levels, often present in urban areas, contribute to a more conducive environment for its formation. Observations suggest that ball lightning may exhibit varied characteristics in urban settings compared to rural landscapes. Brightness, duration, and color may differ based on the density of human-made structures and their materials. Reports indicate that urban ball lightning tends to manifest closer to electrical sources, reinforcing the connection between human activity and this enigmatic phenomenon. Studies continue to explore the potential correlations between urbanization and the frequency of ball lightning events. This ongoing research aims to decode the intricate interplay of natural and artificial forces that shape these transient bursts of energy, contributing to the broader understanding of atmospheric electricity. Advanced atmospheric modeling plays a crucial role in predicting ball lightning events. By simulating the behaviors and interactions of various atmospheric conditions, researchers can generate insights into the circumstances that may lead to the formation of these enigmatic phenomena. High-resolution numerical models allow for the analysis of temperature gradients, humidity levels, and electrical activity within storm systems, revealing potential hotspots for ball lightning occurrences. These models utilize vast datasets, encompassing meteorological observations and historical incidents. They aim to identify patterns that precede the emergence of this unusual electrical phenomenon. Through the integration of physical laws governing fluid dynamics and electromagnetism, simulated environments can reflect the complexities of the atmosphere more accurately. This approach provides a systematic framework for exploring how changes in environmental conditions might influence the development of ball lightning. Observations from lightning strikes and the subsequent atmospheric reactions contribute to the refinement of these models. This iterative process enhances predictive capabilities, allowing scientists to hypothesize about the mechanisms underlying ball lightning. These insights not only aid in cataloging such events, but also foster a deeper comprehension of electrical discharges in the atmosphere. As research continues, the integration of atmospheric modeling with field studies presents a promising avenue for unraveling the mysteries surrounding ball lightning. The implications of climate change introduce new variables into the study of ball lightning. Alterations in atmospheric composition, temperature, and moisture levels can influence electrical behavior within storm systems. This region, where heat and humidity converge, may experience an increase in thunderstorms, subsequently raising the frequency of phenomena like ball lightning. Understanding the interplay between these evolving atmospheric conditions and electrical discharges allows scientists to refine their predictive models. The development of advanced observational techniques enhances the ability to capture elusive ball lightning events. High-resolution imaging and real-time data collection facilitate the analysis of specific atmospheric parameters preceding occurrences. These tools provide invaluable insights into the conditions that foster such phenomena. Collaboration between meteorologists, physicists, and environmental scientists is essential in addressing the complexities of this research. By pooling expertise, it becomes possible to create a multifaceted approach to decode the mechanisms of ball lightning. The integration of interdisciplinary knowledge can illuminate the nuances of electrical phenomena in changing climates. As the planet continues to warm, the quest for understanding ball lightning takes on added urgency. The unfolding changes in atmospheric dynamics may reveal new patterns in electrical behavior, shaping not only scientific inquiry, but also our understanding of the natural world. Understanding the complexities of ball lightning extends beyond the realm of academia. Public engagement plays a crucial role in fostering awareness and appreciation for this enigmatic phenomenon. It acts as a bridge connecting scientific exploration with everyday experiences. By encouraging dialogue between researchers and the general populace, a broader comprehension of atmospheric electricity emerges. Aromational initiatives can illuminate the mysteries surrounding ball lightning, transforming abstract concepts into relatable narratives. Workshops, lectures, and interactive exhibits invite individuals to ponder the nature of this atmospheric anomaly. This engagement not only cultivates curiosity, but also inspires the next generation of scientists and enthusiasts. Increased awareness can lead to more reports of sightings, contributing to data collection and enhancing research efforts. Media coverage further amplifies this dialogue, bringing attention to ongoing studies and discoveries. Documentaries and articles serve as platforms for sharing insights and experiences. As public interest grows, so does the potential for collaboration between scientists and communities. This synergy could expedite the quest for understanding, prompting more rigorous investigation into the circumstances and implications of ball lightning. Through collective awareness, the complexities of atmospheric phenomena become a shared endeavor, enriching both scientific inquiry and the appreciation of our environment. The pursuit of knowledge thrives in a landscape where curiosity reigns, fostering connection between the known and the unknown. Scientific journals occupy a fundamental role in the dissemination of research surrounding phenomena like ball lightning. These publications serve as crucial platforms for scholars to share findings, enabling a scholarly dialogue that transcends geographical boundaries. They provide a structured format for presenting experimental data, observational reports, and theoretical analyses, ensuring that each contribution undergoes rigorous peer review. This scrutiny enhances the credibility of the research, allowing for a more robust understanding of atmospheric electricity. The specialized nature of the journals dedicated to atmospheric science and related fields fosters an environment where innovative ideas can flourish. Researchers may present case studies documenting rare occurrences of ball lightning, detailing conditions under which it manifests, and its potential implications for atmospheric physics. Such articles encourage replication and verification, essential components of the scientific method that solidify or challenge existing hypotheses. Publishing in reputable journals not only amplifies the visibility of this enigmatic phenomenon, but also invites collaboration among scientists. Cross-disciplinary interactions often arise, merging insights from meteorology, physics, and electrical engineering. This collaborative spirit, the interplay between theoretical models and experimental evidence in ball lightning studies, remains a complex and nuanced endeavor. Researchers often rely on a blend of observational data and computational simulations to advance their understanding of this atmospheric phenomenon. Theoretical frameworks propose various mechanisms, including plasmoids and electron clusters, which suggest that this form of electrical discharge may arise under specific environmental conditions. Experimental evidence, while sparse, has occasionally provided glimpses into the characteristics of ball lightning. Controlled laboratory attempts to replicate the phenomenon have yielded mixed results, with some experiments producing glowing orbs under high voltage conditions. These observations have prompted further examination of the parameters necessary for ball lightning formation, such as humidity, temperature, and electromagnetic fields. Researchers continue to refine their models, striving to reconcile theoretical predictions with real-world occurrences. High-resolution imaging techniques and advanced sensors are now employed to capture fleeting moments of these phenomena, adding layers of detail to existing studies. The quest for understanding remains ongoing as scientists meticulously analyze the data collected during transient events. Each observation adds to the cumulative knowledge, yet the elusive nature of ball lightning keeps some aspects shrouded in mystery. The dialogue between theory and evidence persists, reflecting the intricate dynamics of scientific exploration in this enigmatic domain. Advanced sensors play a crucial role in unraveling the complexities surrounding ball lightning. These sophisticated instruments are designed to capture the elusive nature of this phenomenon, often described as transient luminous events. Utilizing high-speed cameras and electromagnetic field detectors, researchers can gather invaluable data on the characteristics of ball lightning as it appears in the environment. High-resolution imaging allows for the observation of its size, shape, and duration. Detailed recordings reveal fluctuations in brightness and color, providing insights into the physical and chemical processes at play. Electromagnetic field detectors complement this visual data by measuring the surrounding electric and magnetic fields, which may interact with the phenomenon. This combination of visual and electromagnetic data paints a more comprehensive picture of ball lightning. In addition, thermal sensors contribute to understanding temperature variations associated with these events. Temperature data can indicate energy release mechanisms and potential materials involved in the formation of ball lightning. The integration of these advanced technologies fosters a multifaceted approach to research. Despite significant advancements, challenges remain in consistently capturing and analyzing ball lightning. The unpredictable nature of its occurrence poses limitations for real-time data collection. Ongoing research efforts continue to refine sensor capabilities, aiming to deepen the understanding of this atmospheric enigma. The relationship between ball lightning and other high-energy phenomena remains an area of keen scientific inquiry. Investigations often reveal that ball lightning appears in association with thunderstorms, a climate characterized by intense electrical activity. This correlation suggests a potential link to the discharge processes that generate lightning. Observations indicate that during such storms, these luminous spheres can manifest, sometimes exhibiting behaviors that defy conventional physics. Research has shown that ball lightning may be connected to more extensive atmospheric electrical events, including sprites and elves. These are transient luminous events that occur high above storm clouds, characterized by their brief yet brilliant displays. The mechanisms driving these occurrences may share commonalities, suggesting an intricate framework of atmospheric electricity where various phenomena interact in complex ways. Studies into the energetic conditions preceding ball lightning events often highlight the role of temperature, humidity, and electromagnetic fields. These environmental factors contribute to the creation of a suitable environment for such anomalies. In some documented cases, ball lightning reported near power lines indicates potential interactions with artificial sources of electricity, further complicating the understanding of its origins. The elusive nature of ball lightning continues to challenge researchers, prompting a re-evaluation of established theories surrounding high-energy atmospheric phenomena. Each new discovery adds a layer of complexity to this mystery, inviting continued exploration into the dynamics of our planet's electrical landscape. Research into ball lightning continues to draw the attention of scientists worldwide, each contributing to a broader understanding of this elusive phenomenon. The integration of advanced imaging techniques and high-speed cameras promises to capture the transient nature of these electrical spheres in unprecedented detail. Observational studies in diverse environments, from urban landscapes to remote wilderness areas, will provide critical data on their occurrences and behaviors. Collaborative efforts across nations are essential, as atmospheric conditions vary greatly in different regions. This global perspective allows for the examination of localized phenomena, expanding the understanding of how environmental factors influence ball lightning formation. The exchange of information and findings fosters a comprehensive approach, merging theoretical models with empirical observations. Incorporating interdisciplinary methodologies, researchers are beginning to explore the connections between ball lightning and various fields, including plasma physics, meteorology, and materials science. Such collaborations may unlock new insights into the mechanisms that govern these phenomena. Additionally, advancements in computational modeling and simulations may aid in predicting occurrences and understanding the underlying principles of their behavior. The quest to unravel the mystery of ball lightning not only enriches our understanding of atmospheric electricity, but also inspires innovative applications in energy and technology. Continued investigation holds the promise of transformative discoveries, shaping the future of atmospheric science. The enduring mystery of ball lightning captivates researchers and scientists alike, a phenomenon that eludes straightforward explanation despite centuries of inquiry. Its unpredictable nature, often occurring during thunderstorms or in the aftermath of lightning strikes, has led to countless reports of glowing spheres that defy conventional physical laws. This region of atmospheric electricity remains shrouded in enigma, challenging established theories of plasma physics and electrostatics. Investigations have uncovered sporadic sightings documented throughout history, revealing variations in size, color, and behavior that further complicate understanding. Some accounts suggest that these luminous orbs can hover, move in erratic patterns, or even penetrate solid materials. The lack of consistent data complicates attempts to replicate conditions conducive to their formation, hindering the development of a comprehensive model. Scientific significance arises from the potential applications of these findings. Understanding ball lightning could illuminate aspects of energy generation and storage, paving the way for innovations in technology. Insights gained from studying this phenomenon may inform safety protocols in storm-prone regions, enhancing public awareness of electrical hazards. As researchers delve deeper into this atmospheric anomaly, the quest for clarity continues. The gradual unraveling of ball lightning's complexities stands as a testament to humanity's relentless pursuit of knowledge, revealing the intricate relationship between atmosphere and energy.